My name is Steffon Luoma. I am the system integrator at Penguin ASI. I have my master's degree in applied physics. I did my thesis at the Sudbury Neutrino Observatory, which is a little stretch from robotics, but it's still, the problem-solving techniques are very similar across from one to the other. I did my undergrad also in applied physics, although it was computational methods, which is how I got into doing computer programming. My thesis was Monte Carlo methods for simulation of galactic supernova detected at the Sudbury Neutrino Observatory. I specialize in data analysis and data collection, sensor integration, and sensor research and development. All the Wi-Fi stuff, I deal with that, setting up the networks and configuring them, setting up the radios and communication schemes. There's a lot of challenges with the teleoperations. You're limited in bandwidth, and it's essential when you're running a machine remotely to have information like video images, audio images, controls going back and forth two-way. And when you're limited with the bandwidth, you really have to have control of the network in meaningful ways. I do a lot of the testing and the debugging simply because I design the interfaces, the graphical interfaces, the communications, and work with the cameras. So it's critical for me to have an understanding on how they look and feel when they're going to be used by the end user. Because I do the sensor integration, I have to work with both sides, the electronics end where they collect the sensor data, as well as the user end where the user has the control. So I guess I interact as an intermediate between the two, and I get to see a larger part of the entire process. So this is our laser scanner made by SICK, and what it does is it shoots a beam of light out, and the beam reflects back into it, and based on the time of flight of the light, it can determine its position, how far it's traveled. So the data from the SICK scanner is merged in with the data from our HORDA, which is the Honeywell Ore Recovery and Tunneling Aid, named after the Star Trek character, I guess. It allows you to know when you moved in any position X, Y, or Z. So you start off and you put in your starting position based on your traditional surveyor, GPS coordinates, or anything like that. And then it can tell you down to centimeter how far you've moved, and it keeps constant track of that. What the inertial measurement unit does is it calculates its orientation in three-dimensional space. So it can tell you by strapping it onto the robot if you're traveling down a slope, which is information you might not have simply from camera information. Our original machines use a fisheye lens on them, which is a really wide field of view lens that allows you to get peripheral vision. So we're moving all our cameras over to a more ruggedized camera like this one here, which is able to submerge in water. It has infrared, so it can see in total dark, which means that we don't require headlights, which saves a lot of power, because power requirement is important consideration in design of our machines. So because we have a lot of different environments we work on, we're shifting the cameras from IP cameras to go into video encoders so that we can basically program it for the video encoder and then exchange the cameras without having to change the code for each type of camera, for each type of situation and environment. So we program the encoder, and then we can swap out the cameras at a moment's notice and change to something for a different environment. The idea in the development from the interface, the user interface end, is to try and make it so that it can be placed where the current machinery is and be as seamlessly transferred, so you can take the knowledge that an experienced miner has learned and just transfer it onto a tele-robotic solution.